Over here, we will try to select the optimal C parameter by cross-validation. So in this code, we are performing hyperparameter tuning for an SVM classifier with a linear kernel using scikit-learn's grid search CV function for cross-validation. This allows us to find the best value of the regularization parameter C among the range of options. As we can see over here, these are the range of our options. So let's understand step by step how this works. Over here we are defining a list param. This contains a dictionary specifying the hyperparameter grid to search over. In this case, we are tuning the C parameter and we are providing a list of potential values to test. In our next line of code, we are trying to create an instance of grid search CV. This specifies SVC. This specify the kernel equals linear. This specifies that we want to use an SVM classifier with a linear kernel as the base estimator for the grid search. Param over here specifies five-fold cross validation, which means the data will be split into five subsets and the model will be trained and evaluated 5 times using a different subset as the validation set each time. Scoring equals accuracy. This we are specifying that we want to use accuracy as the scoring metric to evaluate the performance of different hyperparameter setting. Later on over here, we are training the grid search CV object M on our input data X and labels Y. The grid search will evaluate SVM classifier with different values of C using cross validation and select the best C value based on our accuracy. After we run this code, we get access to the best hyperparameter values and best estimator using the following attributes of grid search CV object M. So we will see in our later code that we are using m dot best params. This will give us the best hyperparameter values found during the grid search, which includes the best C value, and we will see m dot best estimator. This will gives us best SVM classifier with the selected hyperparameter. Let's see what happens in our next line of code. This m.cv underscore results, this attribute of scikit-learn grid search CV object provides detailed information about the cross-validation results for each combination of hyperparameters that were tested during grid search. This information can be useful for analyzing the performance of different hyperparameter setting. So we can find information such as mean fit time, params, standard fit time, mean score time, standard test score, rank test score, information like this. So this mean fit time, what this means is it's an array containing the mean time in seconds taken to fit the estimator on the training data for each parameter setting. Just like that, standard fit time over here is an array containing the standard deviation of the time taken to fit the estimator on the training data. Mean score time over here contains mean time taken to score the estimator. And just like that, standard score time over here is giving us the standard deviation of the time taken to score the estimator on the validation data. Params over here is an array of dictionaries containing the hyperparameter setting for each combination. Param underscore C over here contains an array containing um, values of C parameter that were tested. Just like this, we have more couple of values. Split to test score. This arrays contains the test scores for each fold of the cross validation. And lastly, Standard test score gives us array containing the standard deviation of the test scores across all cross-validation folds, and rank test score over here gives us array of ranks, the parameter settings based on their mean test scores, with one being the best performing setting. In the next line of code over here, we are trying to access mean test scores from the m.cv underscore results dictionary. This code extracts the array of mean test scores for each combination of hyperparameters that were tested during the grid search. As we have seen before, the best params attribute of a scikit-learn grid search CV provides the hyperparameter values that resulted in the best performance during the grid search. In our case, we have performed a grid search to tune the C parameter for an SVM classifier with a linear kernel. Thus, we can use this best hyperparameter value to configure our SVM classifier with an optimal settings for our specific machine learning problem. In our next line of code, we have seen this code earlier. So after running this code, we will have a test dataset xtest with 30 data points having each having two features and corresponding labels. Y test representing two classes 1 and 0. The test dataset can be used to evaluate the performance of machine learning models such as the SVM classifier we have trained earlier or new unseen data. Random.choice method over here. This generates random labels for the test dataset. Uh, It uses this method to randomly select values from the provided array 1, 0. The size of the array is 30, which means we will get 30 random selections of either 1 or 0. Let's work on our next snippet of code. Over here, we are trying to predict y of the test data using best model. So we are using trained support vector machine classifier with a linear kernel and regularization parameter C, which is set to 10 to make predictions on test dataset. And later on, we are trying to compute a confusion matrix to to evaluate the classifier's performance. So we'll check it line by line what's happening over here. Right over here, we are using dot predict function to make predictions on test data x test. The predictions, the predicted tables are stored in the ypred variable. This line of code, what we are trying to do is we are trying to calculate a confusion matrix to evaluate the performance of the classifier on the test data. The confusion matrix function from scikit-learn computes the confusion matrix, and we wrap it in a pandas data frame for a better visualization. Y-test over here contains the true labels for the test data. Ypred over here contains predicted labels generated by SVM classifier. M.classes is used to specify class labels for the rows and columns of the confusion matrix. Thus, this resulting data frame will display the confusion matrix, which provides information about the number of true positives, like here true positive, true negative, false positives, false negatives, allowing us to access the classifier's performance on test data. Moving on to our next line of code, we are trying to create linearly separable data over here. Over here, we are trying to modify the x1 array, which is equivalent to xtest based on the condition where y1 is equivalent to ytest is equal to 1. Specifically, we are subtracting 3 from the elements of x1 that correspond to instances where y1 is equal to 1. This appears to be a data transformation where we are modifying the features of a subset of the test data. Let's dive deeper into this line of code. Over here, this line of code is modifying the elements of the x1 array based on a condition. Specifically, it subtracts three elements from the elements of x1 where corresponding values in y1 are equal to 1. The condition y1 equals to 1 creates a Boolean mask that selects the elements in x1 where y1 is equal to 1. And over here, this line of code subtracts 3 from those selected elements in x1. Thus, this code effectively transforms the feature of a subset of a test data x1 where the corresponding labels are equal to 1, which is y1. In our next line of code, we will try to create a scatter plot to visualize test data xtest with labels ytest. Uh, let's see how this will work. So as we have seen this function before, this line of code is using scatter function from matplotlib, and it's taking xtest as a parameter which specifies the x and y coordinates for each data point in the test dataset. Later on, c equals to ytest determines the colors of the points based on the values in the ytest array. This x label and y label gives us the names of x-axis and y-axis. So over here we have a scatter plot where data points are displayed in different colors, yellow and blue, based on their corresponding labels, and the axes are labeled as x1 and x2. This is allowing us to visually inspect the distribution of our test data and see how well it aligns with the original data or any transformation we have applied. Now, in these lines of code, we will try to train an SVM classifier on our modified test data x1 and corresponding labels y1. After training the model, we will use plot underscore SVC function to visualize the decision boundaries and support vectors for our modified test data set. So this code will help us to access how the model performs on the modified data and whether the feature transformation had any impact on its performance. We are using larger C value in this code, and that's why we are having smaller margin over here. In our next line of code, we are using smaller C value, and thus we will have larger margin in our output. So in this updated code, we are training the same SVM classifier on the modified test data with smaller C value. Thus, when we compare this output with our previous one, we will have larger margin in our smaller C value and smaller margin in our larger C value. This is how this code snippets we have worked on today demonstrate various aspects of using support vector machines for classification, including handling linearly inseparable data, tuning hyperparameters, and evaluating model performance.